All right, welcome students to part 2 of acids and bases. And last time we identified what acids and bases are and how to identify them using several different definitions. And today we're going to expand on that, and mainly today we're going to look at what we call the pH scale, and ultimately there's another scale called the pOH scale as well, and what we use them for. And really one of the main focuses today will be how they're derived. In other words, we hear about the pH scale, and maybe even in another class you've used it in terms of some indicators, and things have turned different colors, and this color means it's an acid and this color means it's a base, and you've been able to identify things like that. But you really, I don't know, or maybe in a pool you used a pH indicator to test the chlorine level in a pool. And the reality is, we're going to take a look at, where do we get the pH scale from in the first place, and what is it we're actually measuring when we're measuring, pH. So let's go ahead and take a look at that and get that started. So as we take a look at our first thing here, we're going to start with water. Water is a unique substance, and water has the ability to react with itself, or do what we call self-ionize. In other words, as water reacts with water, then what you end up with is water can ionize into two different things. And you have what's called a hydroxide ion, which is the OH negative, and the hydronium ion. And I'll circle those here in just a second. Okay, the hydroxide you may already be familiar with, and that's this guy right here. Okay, there's our hydroxide ion. And just so you understand, this guy right here is typically associated with a base. So we're going to write a B for a base there. Okay, so you might want to know that hydroxides are associated with bases. Okay, this guy over here is probably somebody who's new to you. And this ion right here is what we call a hydronium ion. Okay, so this guy right here is a hydronium ion, and we're going to write A for acid. Okay, so this is the ion that we would expect when we're looking at for an acid. So this one right here is what we look for when we look for an acid, and this was the one we look for a base. And what we're saying about water is when water over here interacts with each other, what water has the capability of doing is breaking apart into these two separate ions. One is basic and one is acidic. And so that's basically what we're, and no pun intended there, but that's what we're having happen. Now, where does that leave us? Okay, and I will also say this, well actually we'll get to it in just a second here, so don't worry about that. Okay, where does that leave us? Or where are we going with this? Well, in pure water, okay, that doesn't have anything else in it, the concentrations of both hydronium and hydroxide ions are equal to one another. Matter of fact, let's go ahead and put the concentrations up here. You can see the concentrations of both of them, and these are experimentally derived, and those concentrations are equal to one another. And you'll notice that the concentrations are also very small. 1 times 10 to the -7, that's a very, very small amount. So if I have a bunch of water, most of the water molecules do not self-ionize. Most of them remain as water. Okay, a few of them will ionize into hydronium and hydroxide ions. Okay, and so that's in pure water. Now, if you add something to that water and it's no longer pure water, it's either acidic or it's basic, that's when things begin to change, and that's kind of where the pH scale comes into play. And that is when a substance is either acidic or basic, the concentrations of those ions change. And now if you think about it, if a substance is acidic, so let's say I add or have an orange juice, okay, which tends to be acidic because it's got citric acid in there. Okay, and it does have water in there, obviously, within the orange juice, but it tends to be acidic. Well, which of these two ions do you think would increase? Well, that's right. It would be hydronium. Okay, which one is hydronium? This one right here. Remember, this is hydronium. That's our hydronium ion. And that's the one that would increase because why? It's associated with acids. So as that concentration goes up, then you have something that becomes more acidic. And these two concentrations move in relationship to one another. So as one goes up, the other is always going to go down by the same amount. So however much you increase in your concentration or amount of hydronium ions, you're going to decrease in your amount of hydroxide ions. And vice versa. If something was basic, then you would have more hydroxide ions and you would have fewer hydronium ions. Okay, so it's going to be important in this chapter to remember what goes with what, and you would also want to know and understand that as those concentrations fluctuate, so as one goes up, it's going to either become more acidic or more basic, depending which one is increasing. If hydronium is increasing, then it's going to become more acidic. If hydroxide is increasing, then it's going to become more basic. And that in and of itself is kind of what we base, to tell whether something's an acid or a base, or sometimes what we call how strong an acid or a base is, where it is on the pH scale, as we look at that. However, okay, it is kind of a pain to deal with scientific notation. Matter of fact, we mentioned here that this gives us the ability to measure the concentration of the ions, which will tell us whether a substance is acidic or basic. But just being able to measure, and you'll notice in these real small concentrations and using scientific notation can kind of be a pain in the butt, basically. So what we do is we use some math to come up with what we call the pH scale. Okay, and in your notes, you're going to have the pH scale there. And the pH scale is pretty easy. It's from 0 to 14, and between 0 and 7 is what we call acidic. 7 being perfectly neutral. Anything below 7, okay, would be considered to be acidic, and the closer to 0 you get, the more acidic it is. And then anything above 7, so between 7 and 14, would be considered to be basic. And the closer you get to 14, the more basic it is. And so that's kind of how that scale works. Now, where do we get those numbers, that 0 to 14? Well, if you notice here, okay, if I was to take the equilibrium constant of hydronium and hydroxide here, I was to calculate it out, and they're both 1 times 10 to the negative 7th, then I would end up with 1 times 10 to the negative 14th. Okay? And we said that, even if, let's say, something was acidic, and so your concentration of hydroxide, or hydronium, goes up, and your concentration of hydroxide goes down, they move in relation to one another. So no matter how they change, they're always going to end up, if I did my equilibrium constant, equaling 1 times 10 to the negative 14th, no matter what. So what we can do is we can use a simple little formula, and we're going to do more of this in class. I'm just going to show the formulas to you right now, and we'll talk about the formulas a little bit later. But how we determine pH, okay, or where we get the whole pH scale from, is this simple little formula here. And it deals with a logarithm. Okay, in this case, the pH of something, where we get that whole scale, is the negative logarithm of the concentration of hydronium ions. Okay, so we're not taking into consideration the hydroxide ions, only hydronium ions. And we'll work some problems out in terms of how to calculate. If you knew your concentration of hydronium, how could you figure out what the pH is? And then once you know the pH, you can determine whether it's acidic, basic, or neutral. So we'll do some of that in class. I'm not going to have you do that right here, because there's some stuff we actually need to work through in class, and I need to teach you probably with your calculators. There is actually another scale, and again, I'm just going to show this to you real quickly, and that is the pOH scale. And it's basically the same thing as the pH scale, except kind of flip-flopped, if you want to think of it that way. So again, it's 0 to 14, but in this case, 0 to 7 is, or in between 0 and 7 is basic, 7 is neutral again, and from 7 to 14 is acidic. So it's kind of the opposite of the pH scale. And part of that is because what you're looking at here is the negative logarithm in this case. So it's almost the same formula, but this time instead of measuring the concentration of hydronium ions, you're measuring hydroxide ions. So really what the issue is what ion are you measuring? The most commonly used scale, you don't see pOH a whole lot. It is just kind of another scale that's out there. You can also measure hydroxide ions instead of hydronium ions. It's just more common to measure hydronium ions, is basically the deal. And we'll learn how to calculate both and how to transition from one to the other, one scale to the other. You know, if you knew your pOH, could you find your pH, and how to go back and forth between them. So we will learn all of that in class. Right now, that's the end, and make sure that you take the quiz on Edmodo when you're done watching this video.